Hello and welcome to today's lecture. This is the Comp Sci 201 Section 40 lecture for Wednesday, April 13th in the spring 2022 semester. Today's topics are going to be about systems other than decimal, base 2, base 8, base 16. I will be using Google Chrome, so I'm going to share that. And also going to be using PyCharm. So I will share that. Okay, on to today's lecture. As always, I'll start with some administrative notes. The first is informational. If you have not yet seen the schedule, the final exam for this class is scheduled for Monday, the 23rd of May, from 3:30 to 5:30 p.m. in our regular room, ITE 104. If that's going to be a problem for anybody, you need to let me know as soon as possible. That is what's on the final exam schedule if you look it up. The other sections you may have heard are taking a common final Friday night, the 20th, from 6 to 8. We are taking a different exam from them. You have a different final from the majors, and so therefore we do not participate in the common final, and thus we don't have the Friday night 6 to 8 exam. We have the Monday one. Homework 6 is out. I want to talk about it in just a minute or two. We'll go into some detail on that. And Project 2 has been released. You should be working on it. I will talk more about it. It is due the 25th of April. You have almost 2 weeks left. And a reminder that we have a test next Wednesday, the 20th, after I'm back from Colorado. This exam is comprehensive because it has to be. You can't forget what an integer is. You can't forget what a string is, things like that. But it will focus on the new material since the exam 1. It is, as I've mentioned before, the same format as the previous exam. You can count on 10 multiple choice or true false questions. You can count on 8 short answer questions, and you can count on 2 short programming problems worth 100 points. I will later this week post a sample exam 2 to the GitHub repo, hopefully the next day or so, and I will go over it on Monday. Monday the 18th is a review day. I will be physically there in the classroom. We can talk about the sample exam and any questions you might have. Now, as I mentioned, I want to talk a little bit about Homework 6. Homework 6, I very briefly raced through in the Monday lecture. It is on recursion, which we covered the last 2 days. I recognize that some people immediately grok recursion and understand it. Others have difficulty with it. That's fine. That's why we teach the class. The key in successful recursive programming is to quickly identify the cases, the base case and the recursive cases, and what you want to do. Based on some comments I've been reading on the Discord channels, I wanted to talk briefly about problem 3. I'm not going to give you the answer, obviously. You'll have to do that yourself, but I could probably sketch out some things you have to do. Now, problem 3 says you have to write a recursive function in a file called slice_replace.py. When you submit the homework, you will submit a file called slice_replace.py, which will contain a function exactly as shown here. Def slice_replace with 3 parameters, big underscore string, find underscore string, and replace underscore with. You must submit an answer that has the function signature, the function name, and parameters exactly as you see here. Otherwise, the test code won't work, and that doesn't do well for your grade. So let's talk about how you do this. Now, the function takes the big string and goes through it character by character. And anytime we find the find string in the big string, we replace it with the replace string. For instance, if I run slice replace on the string hello Ella, and I look for an EL and I want to replace an EL with X every time it occurs, what you see on the line here is the response. You would go the H, the E, the L. Hey, that matches the EL. Replace that, it becomes HXLO. Continuing on, the EL and Ella will be matched and replaced with an X. A second example, slice replace with the ABs and change all the AB occurrences into Cs. Okay. Now the hint given is you can use slices to do string comparisons. That'll make it easier. Slicing the big string and so on. Okay. Now let me explain what this means. So let's go to our friend pie chart, and we're going to write some pseudocode. Okay. You have to write def find underscore replace with parameters big string, find string, and replace with. And again, don't change that signature. You have to submit a function that is called exactly like this. Base cases and recursive cases. Let's talk about the cases we need to consider and what we do for each case. Here's a simple one. Sorry. Here is a simple one. If the big string is shorter than the find string, we know we cannot match the find string. In other words, if I have a 3-letter string ABC and I'm looking for some string that is 4 letters long, ABCD, you can't match. Okay, you can't match. So the first case is simply you need to address what to do if the big string is shorter than the find string. Okay, so you're going to write code that considers the big string is shorter than the find string. How do we tell if it's shorter? We use length, right? That's going to be something like if length of big string is less than length of find string, you simply return the big string. Because there's no match, and if there's no match, there's no replacement. And if there's no replacement, that's fine. Now let's consider case 2. Case 2 is that the first few letters of big string are an exact match for the find string. In other words, we found what we're looking for. It's an exact match. This is what we need. What we do then is we make the replacement, and then we recursively call the function with the rest of the big string. This is the hint that you saw on the assignment. Okay. And then you're going to append the replacement to the result of the recursive call. Okay. Relating to the hints in the assignment, what we're doing is something along the lines of if big string from 0 to the length of find string is equal to find string, we have a match. Replace big string from 0 to length of fine string with with then call find replace with big string from length of find string to the end, find string and replace with. So when the assignment said as a hint, you can do the comparisons using string slicing, that's exactly what we meant. We took a string splice right here. This is a string slice, these characters, and we used it to do the comparison, and we found an exact match. So then we did the replacement using string slices, and then we made our recursive call using a string slice with the rest of the string that wasn't replaced. Okay, now be very careful with this index. This is the original length of find string. This is the original big string. This is the original length of find string. Make sure you have not changed anything before you make this recursive call. Otherwise, you'll have to adjust your indices. Okay, if you do, not a big deal. It's just a matter of playing around with it for a little bit. So that's the first two cases. Now the other thing is case 3. Okay. Case 3 is simply that the first letter of big string does not match the first letter of fine string. Obviously, then there's no replacement to be made. Move on to the next letter and recursively call find replace with big string. Just drop the first letter. Just drop the 0. Again, this is the hint in the assignment. Big string from 1 to the end. Find string. Replace with. And of course, make sure to append the original first letter to that result to get the final string. Okay, so realistically, when you're doing problem 3 on homework 6, make sure that your code for def find replace covers these 3 cases. The first case is if the big string is shorter than the fine string, you simply return the big string. That's it. You're done. There can be no more replacements. The second case you have to consider is if there is an exact match. The first appropriate number of letters of big string are an exact match for fine string. We found a match. We need to make the replacement. Okay, make sure that you append the replacement to the result of your recursive function call, where you do the recursive function call like this. Okay, so that's the second thing you need to do. Second case you need to make sure you cover. The third case, not a match. The first letter of big string is not a match for the first letter of fine string. There's no replacement. Recursively call find replace, just dropping the first letter, so from 1 to the end, and then make sure again you append that original first letter. When I say append the first letter, what's going to happen, again, just most of you I think understand this, but all this means is if I have the original string A, B, C, D, E, what I want is to append the string A concatenated with the result of find replace B, C, D, E bind string replace with. Make sure you do that concatenation. Okay, so that's what I mean in both cases 2 and 3, where I said either replace or make a recursive call and make sure you concatenate, you prepend the letter or letters that you dropped. So that's a hint on problem 3 on the recursive homework 6. If you have questions, get help, office hours, Discord, what have you. It's I think most people find it daunting because they simply are not sure about recursive cases. They're not comfortable with base cases and recursive cases, but it's really, once you identify the cases to cover, it's really not that bad. And in this case, you have the 3 cases that I mentioned above. Okay, with that, let's get back to today's lecture. So today's lecture, as I said, is numbering bases with computers. As humans, we have generally always done things in powers of 10. We count 10, we count 100, we count 1,000. We have 10 symbols used to count. Any number can be expressed in a combination of the 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The reasons we do this are fairly obvious. Most humans have 10 fingers. Most humans have 10 toes. Therefore, that seemed a natural way to keep track of things by, using your fingers. How many of these have you got? And that was how the base 10 numbering system came. And humans have been using it forever. And it's natural for us. But computers, machines, don't work that way because they don't have 10 digits. They don't have 10 fingers or 10 toes or 10 states. Computers and very similar machines are simply a series of electrical switches. At a high level concept, a computer is simply a series of electrical switches that are turned off or on to allow electricity to flow. Current can flow. Voltage states are set to one level or another. Since electricity and magnetism are related, if you've studied physics, you can do the same thing with magnetic fields. And all of these things basically have 2 states. An electrical switch is on or off. The electrical current is flowing or it's not flowing. The light bulb is on or off. It's a magnetic north pole or a magnetic south pole. The voltage is +5, the voltage is -5. All of these are relevant in computing in the hardware case. And so we simply adopt the convention that if something is on, it has the value 1, and if it's off, it has the value 0. And I am not that old, contrary to some rumors, but in the original computers, people actually had to program computers by continually flipping switches. You would set an array of switches into your on or off, up or down positions, and then you would flip another switch that let that load, and that was how you programmed the computer in all ones and zeros. Now, anything that only has ones and zeros is called binary. Binary, base 2, we only need the 2 digits to represent all numbers using powers of 2. And so in binary, there are only 2 binary digits. Computer scientists are lazy. I am one. I can say it because I am. We look for shortcuts all the time. Binary digit is a pain to say. So you can shorten it a little. How do you shorten binary digit? To bit. So if anybody ever asks you where the term bit came from, bit is simply a shortening of binary digit base 2. Okay. So there's an old joke, sorry, I have to repeat it. I think it's in my contract somewhere, that there are 10 types of people in the world, those who own binary don't understand binary, and those who don't. I apologize, it's a bad joke, but it is. So computers speak in base 2, humans speak in base 10. How do we convert? The short answer is to recognize that just like in base 10, we read binary numbers from the least significant bit or least significant digit on the right to the most significant or largest on the left. Now, if I look at this 1 right here in a base 2 number, that is the number, same as it is in base 10. If I were looking at this in base 10, I would say that this is 10,000,001, right? Because this represents 1, this represents tens, this represents hundreds, this represents thousands, this represents 10,000s, 100,000s, millions, 10 millions. So if this were a digital number with base 10, this would be 10,000,001. Now, the same idea exists in binary, except instead of multiplying everything by 10, we multiply it by 2. So I've kind of illustrated down on the bottom of this slide that what we do is we take the least significant value on the right and work our way to the left, multiplying by 2 every time. So this least significant bit, this digit on the right, is how many 1s do you have? The next one is how many 2s do you have? 2 times 2 is 4. So this represents how many 4s do you have? 4 times 2 is 8. So this represents how many 8s do you have? 2 times 8 is 16. How many 16s do you have? How many 32s do you have? How many 64s do you have? How many 128s do you have? So in this case, we can see we have 1, 128, and 1, 1, giving us this value, 1, 0, 0, 0, 0, 0, 1 in base 2 is equal to 129 base 10. Okay. So another example, 1, 1, 1, 0, 0, 1, 1, 0. Again, we start here. We have 0 1s. We have 1 2. We have 1 4. We have 1 8. We have a 16. We have a 32, or 0 16s rather. We have a 32. We have a 64, and we have 128. So if we want to find out in base 10 what this number equals, then we can say in base 2, 1 1 1 0, 0 1 1 0 is equal to 230 if we add them all up. Okay. Now, binary math works just like decimal math mostly. If you're adding them, you add numbers starting on the right and you carry when appropriate. 1 0 1 0 plus 1 1 0. 0 plus 0 is 0. Now, 1 plus 1 is 10, which just like with decimal, it's 0 carry the 1. So we get a 0 and we carry a 1 over here, and 1 0 1. Hey, that's 10. That gives us a 0, carry a 1. 1 and 1 is 0, carry a 1, put the 1 down here. And so 1 0 1 0 plus 1 1 0 is simply 1 0 0 0 0. So it's exactly the same principle as with base 10 adding. Start in the rightmost column, add the numbers, and carry over to the next column when appropriate. Subtraction is similar. You start on the right again, and when needed, you borrow from the next place over. 0 minus 1, you can't do that. There's no negative 1. Negative 1 is not a number in base 2. 0 or 1, no negative 1. So what you would do is you borrow the 1 from here and you'd say, 1 0 minus 1, that's a 1. That now leaves the second bit to be a 0. 0 minus 0 is 0. 1 0 minus 1, again, borrowing, we get 101. Multiplication and division, we won't get into the work. So converting from decimal to binary, we've already shown. It's a simple matter of saying, okay, every position is a power of 2 more than the other. Decimal to binary is the same idea, but you need to figure out how the decimal digits relate to the powers of 2. So in that case where I had 1 0 0 0 0 0 1, 10,000,001 base 10, and I ask you to tell me what it is in binary, what you have to do to figure out how much it is in binary, if you did it on your own, is figure out the powers of 2. and you subtract until you get 0. Okay, so what is the largest power of 2 that's less than 10 million and 1 base 10? Well, if you do the math, the answer is 23. 2 to the 23rd power is equal to 8,388,000. 24 is that's too high. Okay, so you would put 1 in the 23rd position, and that is you subtract 8,388,608 from 10 million and 1, leaving you 1,611,393. Okay, so we have a 1 in the 2 to the 23rd place. Now we have a 0 in the 2 to the 22nd place because that won't fit. We have a 0 in the 2 to the 21st place. That won't work. But 2 to the 20th. Okay, 2 to the 20th will work. When I do that subtraction, I get 562,817. Okay, and so I keep going, and what I'm going to wind up with is this binary string. This is 2 to the 23rd. There are 24 bits in this string, and you get 1 in the 22 to the 23rd place, 0, 0, 1 in the 2 to the 20th, 1 in the 2 to the 19th, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, a bunch of zeros and 1. This is base 2 representation of the decimal number. Okay. Fortunately, we'll get to it in a minute, Python handles a lot of this for us. Python represents these numbers and makes it so much easier. Okay. To indicate that a number represents a binary number, preface it with 0b. So if I say x equals 0b, 110111011, this tells Python I want the base 2 number. Hey, Python, I do not want the base 10 number. I want the base 2 numbers. And you can use a built-in function to convert decimal to binary. Okay, and you can convert to base 10 by using int. So very quickly into PyChart, let me create a new file. And I've already used the name April 13th, so I'm going to call it this way. Okay. This is in class coding for April 13th, converting between base 2 and base 10. Okay. To make it clear to Python, this is base 2, use 0b. So x equals 0b 11011101. X is now a binary number. Okay. Print x. Okay. And what will happen when we run this code is that Python automatically converts this for us into a decimal, a base 10, and tells us that this is equal to 221. Okay. If you don't tell it to print the binary, Python will automatically assume you want the integer because most people understand 221 a lot better than 11011101. Okay. If you want to take there is a way to print out the binary if you really want to. I don't think I've got to spend a lot of time on that because it's not something that's done very often, except to say that, ooh, yes, you can do it. If you want to convert something, you would say, okay, let's go to a Python console. Let's get rid of this. Let's say that I equals 254, which is a decimal number. Now let's say that bin I equals apply the function bin, or binary, to I, which converts it to bin. And what is the value of bin I? And now you can see that it will print out the binary. It converted to 54. Python converted using this function bin to binary, and now it prints it out and it tells you it's a 0B. Okay. So you can play around in Python and get what you want and do conversions. Again, it's important to understand that realistically, the computer is not doing math using base 10. The computer is converting everything to, at the lowest level, base 2, and doing the math that way, and then converting back to base 10 because it understands that it speaks a different language than you do, and it does the automatic translation. Now, things are big numbers. We talked about the 10 million and one. Okay, let's come back here to PyChart with the Python console and say that I is the decimal number 10 million and one. Now we convert using bin I, using the binary. We convert to a binary number, and you can see it's a big honking thing. And hopefully it's the same as I showed you on the slide, and my math was correct, because it's more likely that Python is correct than me. That's a big number, and that's very hard to deal with for a human being. So when humans do have to speak the same language as computers, when humans have to get out of their comfort zone and get away from base 10, we use a base 16 or hexadecimal, hexadecimal meaning 16, or hex for short. Okay, so when someone says they're talking about hex, that means they're simply using a base 16 numbering system. Now, for binary, we needed 2, 0 and 1 symbols to represent numbers. For decimal, we needed 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 symbols to represent numbers. For base 16, we now need 16 symbols to represent all of the possible hexadecimal digits. Okay, and so here's the convention that's been adopted. We start with the 10 we already have, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for the next 6, we use the first 6 letters of the alphabet in order. So A in hex is 10 in decimal. For 11 in decimal, we use B. For 12 in decimal, we use C. For 13, we use D. 14 is E, and 15 is F. And now we have all the symbols we need, 16 of them, to represent everything we need in base 16 arithmetic. Okay. The algorithm is similar to binary. Fortunately, there's a built-in function in Python that does the conversion for us. It's called hex. Hex returns a hexadecimal value. Now, just like 0B tells Python that this is a binary number, 0x means it's a hexadecimal number. So let's go back to PyChart. Let's take a hex number, or let's take a large decimal number. I equals, once again, 10 million and 1, 2, 3, 4, 5, 6, 7. Now, let's say hex I equals the function hex built in, convert to hexadecimal. And what is the value of hex I? Python prints out 0x to show us that this is a hexadecimal number. Python is telling us this is a hexadecimal number. 5F, 5E, 101. Now, syntax, sometimes you will see these A, B, C, D, E, F in uppercase. Sometimes you will see them in lowercase. It doesn't matter as long as you're consistent. PyCharm chooses to use the lowercase representations. I've seen other versions that use the uppercase. Again, it doesn't matter. I tend to use uppercase in class. I know that PyCharm tends to use the lowercase. Other implementations, it doesn't matter. They're the same. Okay. So this is a way of creating something. They're converting something in Python from decimal to hex. Converting back, again, is straightforward. And in fact, sometimes it's automatic. X equals a hexadecimal number, 0x, 1, 2, 3, 4, 5. Print X, and Python automatically converts this hex number to the decimal number 74,565. Going back to the slides, the algorithm is the same. Remember that. Let me put another slide in here real quick. Basically, it's a simple matter of saying 0x A, B, 1, 2, 3. This represents ones, or 3 times 16 to the 0 power, or 3 times 1. Then 2 times 16 to the first power, or 3 times 16, or 48 in base 10. Then 1 times 16 to the second power. 16 squared is 256, so this is 2 times 256, which is equal to 512. Then you'd have B, or 11 times 16 to the third power, and then A, or 10 times 16 to the fourth power. Now, 16 to the third power is 4,096. If I haven't made a math there, so this is 11 times 4,096, which comes out to be 45,056. 16 to the fourth power is 65,536. And so we have 10 times that. And that is simply 655,360. So you would then add up those numbers, and 0xAB123 is 3 plus 48 plus 512 plus 45,056 plus 655,360, and that's equal to whatever that is. Okay. Now, so we've talked about converting binary to integer. We've talked about converting hexadecimal to integers. Fortunately, you do not have to go through decimal to convert binary to hex. And in fact, it's a very easy thing to do. And it's a very important thing to do, because computers only operate with binary digits, zeros and one, and because computers deal with billions to trillions of these zeros and ones, it's very important to be able to group them. It turns out that 4 binary digits, 4 bits together, represent exactly 1 hexadecimal digit. After all, 2 to the 4th is 16. So if I have 2 symbols, 0 to 1, to represent 1 bit, then 2 to the 4th, or 16 symbols, will let me represent 16 different values, and 16 values is hexadecimal. So if you are converting between binary and hex, if you start with binary, you simply replace 4 bits with their hex equivalent. So I would take this long string of 24 bits that I had earlier, this 10,000,001 base 10, came out to this 24-bit string you see here on the slide, I simply break up the 24-bit string into 6 groups of 4 bits, and then I convert each 4 bits into hexadecimal. Starting from the left, 1001 binary is 9 hex. 1000 is 8. 1 is again 9. 0110 is 6. 1000 is 8 again, and 0001 is simply 1 in hex. So to convert the binary string, which had 24 bits, into hexadecimal, it's simply 0x to indicate its hex, then 9869681. So it's very simple for computers, and in fact humans, to convert binary to hexadecimal and back, and vice versa. How did I get that conversion table? How did I get the conversion so easily on that slide? Very simple. Here's a table, okay, mapping the binary value to its appropriate hex value and its appropriate decimal value. You just learn this table. After you do it a while, it becomes second nature. You know, occasionally you might have to go, wait, is C 13 or 14, 10, 11, 12, 13? Okay. But, you know, it becomes second nature. Okay. The last thing we'll talk about used to be important, but is less so now, and that's called octal. When computers had fewer bits, octal was more important. For now, it's not a big deal. Octal is base 8. The symbols that are needed are 0, 1, 2, 3, 4, 5, 6, 7. They are represented in Python as 0, and then the number. That's a number 0, then a lowercase letter O, and that means that it's an octal number. And the last slide covers things I've already done. So again, in PyCharm, if I want to say an octal number, I can say, okay, y equals, again, 0, lowercase o, and then allowable symbols are 0 through 7, 7, 7, 7. Okay. Hex y equals hex of y. And what is hex y? Is 0x1ff. So to convert the octal 777 octal is 1ff hex, and we can convert back and forth. You will rarely in your computing life see anybody use octal digits. We cover it because it does exist, and every now and then there is somebody who doesn't. But what's important to know from this lecture is, unlike humans, computers operate on base 2. Okay, because computers operate on switches are on or switches are off. It is a magnetic north pole or it is a magnetic south pole. The voltage is plus 5 volts. The voltage is minus 5 volts. Okay, even optical computers operate on there is a photon or there is not a photon. It's all base 2. There have been people try to do some weird things with base 3, but they tend to be research efforts or toys. Every practical computer you're going to run into works on base 2. So you need to understand that binary exists so that you can understand how and why certain things happen, which I will demonstrate in a minute. Okay. And then hexadecimal, because it's a lot easier to group bits in groups of 4 and replace 24 long strings of bits with 6 hex characters. So you will see hex a lot. And the key thing to remember there is 0x means it's a hex number. Okay. Now, why is it important to understand that computers operate in terms of bits? Suppose I have I equals 1 divided by 3, bin I equals bin of I. Oops, sorry, that only converts from integers. You can't convert floats. Okay, we will skip that and move on from that. The point is, because computers represent things in binary, some math that works out famously in decimal will fail to work in computers. And so you can get examples of things that you know the answer to, the computer will happily tell you is wrong. And that's because it's the base 2 rather than the base 16, and that was an unfortunate example. We'll get to that. Okay. So that will be all of this lecture. What we have covered is some hints, some discussion of one problem on homework 6 to think about the cases you need to cover, the recursive cases and the base cases, and how to get that working. And other than that, that problem is simply string manipulation. You know, it's simply string splicing and string concatenation. Once you get the cases down, and the other homework problems are pretty much the same. We can talk about them. It's due, the homework is due next week, next Monday night. Again, work on it. You have Project 2 to go on. There will be a video on Project 2 on GitHub for you to see. With that, thank you very much. And we will stop at this point.